Welcome, everyone. In today's lecture, we are going to dive into a truly powerful tool for managerial decision-making. We're going to learn how to take a complex, messy business problem, one with all sorts of competing priorities and variables, and systematically boil it down to a single, optimal, data-driven solution. Now, I want to be clear. This is not just some abstract mathematical exercise. This is a foundational skill for any of you who want to become effective managers. We're going to learn the language and the logic of matrices, and specifically, how to get to something called Reduced Row Echelon Form. So here's our game plan for today. It's structured to really build your understanding from the ground up. We'll start by looking at a realistic dilemma a manager might face. From there, we'll see how to translate that problem into the structured language of matrices. Then, we have to define our goal. What are we even trying to do? That's RREF. After that, we'll get into the nitty-gritty, the procedural steps, which are called row operations that get us to that goal. And finally, the most important part, we'll translate our mathematical answer back into a clear, actionable business decision. All right, let's begin by grounding ourselves in the reality of the business world. The situations you're all going to face in your careers are rarely simple. They're almost never about just optimizing one single thing. You're constantly going to be in a state of balancing numerous, often competing pressures. Now, this question is really at the heart of so many business disciplines, operations, finance, you name it. Just imagine for a second that you're in charge of a product line. Your marketing team is telling you they need a bigger budget to drive demand. At the same time, the finance department has just mandated cost reductions across the board. And to top it all off, your supply chain manager is on the phone warning you about a shortage of raw materials. See, an intuitive decision here, a gut feeling, is really just a guess. And in business, a guess can be incredibly expensive. What you need, is a method to honor all of these constraints at the same time. So let's make this real with a case study that will follow for the rest of this lecture. I want you to put yourself in the shoes of this cafe manager. You have very explicit constraints. First, you know you have to order a total of 125 kilograms of coffee to meet your weekly demand. That's non-negotiable. Second, your budget is capped at $1,000. Let's say your premium blend costs $10 per kilogram and the standard blend costs $6. Third, your storage room is not infinite. It can only hold 15 cubic meters of product. And the premium blend takes up 0.1 cubic meters per kilogram, while the standard takes up 0.15. So the question is, how do you figure out the exact amount of each blend to order? This is the problem we are going to solve today. So the very first principle of solving any complex problem is organization. We have to translate the story of our business problem, all that narrative, into a standardized mathematical format that's rigorous and, frankly, much more efficient to work with. Sure, we could write all this out as 3 separate equations. If we let X be the kilograms of our premium blend and Y be the kilograms of the standard, we'd get something like this. X plus Y equals 125. That's our demand. Then 10X plus 6Y equals 1,000. That's the budget. And finally, 0.1X plus 0.15Y equals 15 for storage. Now, you could probably try to solve this with substitution or elimination, the stuff you learned in high school algebra, but just imagine if you had 10 different coffee blends and a dozen constraints. That system of equations would become an absolute nightmare, and it's incredibly prone to error. We need a better way, a more scalable and systematic approach. And this is where the sheer elegance of a matrix comes into play. What you're looking at here is called an augmented matrix. Let's break this down very carefully. Each row represents one of our constraints, demand, budget, and storage, in that order. Each of the first 2 columns corresponds to one of our variables. The first column is for our premium blend, X, and the second is for our standard blend, Y. The numbers you see are simply the coefficients from those equations we just talked about. That vertical line in the middle, you can just think of that as a big equal sign. And that final column holds the constants, the targets we're trying to hit. See how that works? All the clutter is gone. We're left with a clean, numerical grid that represents our entire business problem. Okay, so we've got our data neatly organized in this matrix. But what does a solved matrix even look like? We can't just start randomly changing numbers. We need a clearly defined target state, a finish line, where the answers become totally obvious. In linear algebra, we call this state Reduced Row Echelon Form. I want you to think of RREF as the ultimate simplification of our problem. It's a very specific, very organized structure that is mathematically equivalent to our original system, but it's been arranged in such a perfect way that the solution requires no more calculation. Our entire goal from this point on is to methodically manipulate our starting matrix until it conforms to the strict rules of RREF, and in doing so, we'll reveal the solution that's currently hidden inside those numbers. These 3 rules, this is our constitution. This is everything. Let's really examine each one. Rule 1, the leading one, is about creating a unit basis. It essentially turns a complicated statement like 10x equals into the much simpler 1x equals, which is exactly how we want to state the value of a variable. Now, rule 2 is, in my opinion, the most critical. Any column that has one of these leading ones must have zeros everywhere else. This is the act of isolating a variable. It makes sure that the value of x, for instance, is stated completely independently of y. And rule 3, the staircase pattern, just ensures the matrix is organized in a logical cascade. It prevents contradictions and makes the whole system easy to read from top to bottom. Okay, we have our starting point, our messy matrix. We have our destination, that clean RREF matrix. Now we need the vehicle to get us there. We need a set of legal moves, operations that let us change how the matrix looks without changing the fundamental truth of the equations it represents. And these are known as the elementary row operations. This is it. These 3 operations are your entire toolkit. You don't need anything else. The first one, swapping 2 rows, is purely organizational. It's like reordering your to-do list. It doesn't change the tasks. The second one, multiplying a row by a non-zero number, is how we're going to create those leading ones we just talked about. It's like saying if 10x plus 6y equals 1,000, then it must also be true that 1x plus 0.6y equals 100. The relationship is perfectly preserved. The third operation is our powerhouse. It's our primary tool for creating all those zeros. It lets us cleverly combine the information from 2 different constraints to simplify one of them. Mastering the strategic application of these 3 moves is the key to this entire method. Now, I cannot stress this point enough, so please listen carefully. This is the single most common source of error for students learning this for the first time. A row in a matrix is a complete equation. It's a complete thought. If you perform an operation on it, let's say you multiply by 1/10 to create a leading one, you must multiply every single element in that row by 1/10, and that includes the number on the far right after the augmented line. Forgetting to do that is like changing your budget formula without changing the budget itself. It completely breaks the mathematical integrity of your system and guarantees you will get the wrong answer. Be meticulous here. All right, let's actually begin the process. Our very first objective is to get a leading one in the top left position. We call that the pivot position. Now, if we look at our matrix, we see we already have a 1 there from our demand equation. So that step is actually done for us. This is a bit of good fortune, but if that number had been, say, a 5, our very first move would have been to multiply that entire first row by 1/5. Okay, now we apply rule 2. We have our leading 1 in place, so our next job is to make every other entry in that first column a 0. Let's look at the second row, which starts with a 10. Our strategy is to use row 1 to eliminate that 10. We're going to perform this operation. Take row 2 and subtract 10 times row 1 from it. See how that works? 10 minus 10 times 1 gives us the 0 we need. But remember our warning. We must apply this operation to the entire row, carefully calculating the new values for the y column and the constant column. Then we repeat a similar process for row 3 to get rid of its first term. And just like that, we've successfully isolated our first variable. Now, we would just continue this process. We'd move down to the second row, second column, work on creating a new leading 1 there, and then use that new leading 1 to create zeros above and below it in the second column. After a series of these precise, logical steps, we achieve this remarkable transformation. On the left, you see our initial chaotic problem. On the right, the perfectly ordered, perfectly clear RREF matrix. This isn't magic. It is the result of a systematic, repeatable algorithm that guarantees a solution if one exists. So, we've done the heavy lifting. We've completed the mathematical procedure. But as business students, our work isn't done. The crucial final step is to translate this final matrix back into a concrete, actionable business decision. What does this elegant grid of numbers actually tell us to do? Well, the absolute power of RREF is that this translation is now trivial. It's incredibly simple. Let's just read the top row together. It says 1 times X, our premium blend, plus 0 times Y, our standard blend, equals 50. In plain English, that means order 50 kilograms of the premium blend. Now let's read the second row. 0 times X plus 1 times Y equals 75. The instruction, order 75 kilograms of the standard blend. All of the ambiguity is completely gone. Now, I want you to really consider the power this gives you as a manager. When you present this decision to your boss or your team, you're not relying on a hunch. You're not hedging your bets. You can state with absolute certainty that this specific order,
50 kilograms of premium and 75 kilograms of standard is the only combination that perfectly satisfies all three of your business constraints. It meets the 125 kilogram demand, it stays within the $1,000 budget, and it fits inside your 15 cubic meter storage space. This gives you a single, optimal, and most importantly, a completely justifiable path forward.
And this is exactly how you communicate that decision, not with uncertainty, but with the authority that comes from rigorous analysis. You can walk into a meeting and say, "The analysis is complete. The model accounts for our constraints on demand, budget, and storage. The optimal solution is to order 50 kilograms of premium and 75 kilograms of standard. Let's execute." That is the sound of competent, data-driven management. This framework, this way of thinking, it extends so far beyond our little cafe example. Think about production planning, balancing machine time, labor hours, and raw materials to hit production targets. Or think about financial portfolio management, allocating capital across different assets to maximize your return while sticking to your client's risk tolerance. You could even use it for marketing campaign allocation, figuring out how to distribute an advertising budget across digital, print, and TV to get the most customer reach. The point is, any business problem that can be modeled with a system of linear constraints is a candidate for this incredibly powerful solution method. This tool is not just something to learn for a final exam. It is a fundamental asset for your entire professional career.